Hi, this is a quick review for your test 3. Now, to make the video not so lengthy, I'm going through a solved out key, but I'll walk you through the steps of setting up each problem. So the first problem, it's pretty straightforward. It's setting up your integration. Now, remember when you integrate, you always want your high value, your higher bound, and then you want your lower bound. So we're integrating in terms of, for x, we have 6 and 1. For y, we have 9 and 5. And we're integrating over xy. Now, because it didn't tell us an order of integration, we're free to choose that upon ourselves, given the different type of problem. Now, because there are only constants here for both x and y, any order is fine. So I did dy dx. So for y, we have our limits from 9 to 5, and for x, we have our limits from 6 to 1. And then we integrate accordingly. And sometimes it's okay if you split them up. When you have constants and if they're being multiplied, you can go ahead and split your integration, just like you learned back in your calculus 1 or 2. And we go ahead and integrate. You see the steps there, and your answer should be 490, which is B. Next question 2, it reads, find the average value function f over the given region. Our question reads, f of x comma y is equal to 5x plus 9y over the triangle with the vertices with the vertices 0, 0, 8, 0, and 0, 2. And here we have a picture. We have 0, 0, 0, 2, and 8, 0. And we see the enclosed triangular shape. Now we want to find an equation for which we can integrate over. Now you can use type 1 or type 2. If you choose type 1, then you're looking at your x value. So we'd go for our x's from 0 to 8, and we integrate from 0 to y equals negative 1/4 x plus 2. Now, if you want to do type 2, then we're looking at the y's. We go from 0 to 2 for y, and then we integrate the line in terms of x. So we have x equals 8 minus 4y. And that one's nicer. Type 2 is much nicer because we don't have that one negative 1/4 fraction. And to create this line, you can go ahead and use regular y equals mx plus b, find your slope. What I did was, well, if we have an intercept, a y-intercept of 2, so I know my y-intercept and my slope is down 2 over 8, down 2 over 8, so that gives us negative 1/4 for our slope. So I came up with this line, and I saw that we had our fraction, which was a turn off, so I made it, I thought about, well, what if we work in terms of another variable instead? Okay, so to integrate, we're doing type 2. Type 2 is kind of another word to saying in terms of y, so we want to go ahead and have y second and x first. And yes, that does matter. It depends if it's type 1 or type 2 integration. This is back from section 5.2. Okay, once we integrate and we have set up our bounds based on our image, we can go ahead and integrate again on our function f of x comma y, which is 5x plus 9y. Now, be very careful of your instructions so you don't go crazy. It's asking for the average value function. Now, your formula says you have to go ahead and find your area and write 1 over your area. To find your area, you integrate over your same bounds by 1. You should get 8. So since we want 1 over your area, you get 1 over 8. Or you can just find the area of your triangle. Your area of your triangle is 1/2 base times height. So we have 1/2 times your base of 8 and your height of 2. So your area is 1/2 times your base, which is 8 units, times your height, which is 2. And you also get an area of 8. So that's the beauty of math, that it just always works out accordingly. All right, so this first integration is what I did first. I did first focusing on the x's, And I show every single step so that we don't get lost. I know integration, at least for me, I always make the silliest algebra mistakes. So I would truly recommend you to be careful. Once you find your answer, remember that we want the average value. So it's our answer divided by 8 or times 1/8. And that's how you get your desired answer for this one. All right, next question. Change the Cartesian integral to an equivalent polar integral, then evaluate. So when you want to work with polar integrals, remember it's always r dr d theta. You first need to integrate in terms of r and then theta, but you need to also include that constant variable of r. Another helpful trick when you're working with polar integrals is x squared plus y squared equals r squared. And other values, just such as the value of x and y. It's also helpful to know. But for this question, that's all we need. Now we have our integral set up. Now we look at our bounds. First, we look at x. We have x is equal to square root of 9 minus y squared. Okay, let's take a look at what we have there. That's really x squared plus y squared equals 9, which is a circular radius 3. Okay, so this can help us find into a polar coordinate. So polar coordinates are ideal when we have circles. And they're ideal because with circles, those radicals come to play when we evaluate for or solve for one variable, just as we saw here. And that can be problematic because with radicals, we're forced to use U sub, but sometimes U sub isn't something we can work with because of our integrand. All right, when you're setting up your polar coordinates, you always want to look at your R. So for your R, you look from your center to your endpoint. Now our endpoint is r equals 3. And we got that for our equation x squared plus y squared. That gives us r3. Now we want to look at the measurement along the angles. So we see that it's a full circle, so it's 2 pi. So it tells us that for r, we see that for r we go from 3 to 0. And for theta, our angle, we go from 2 pi to 0. And now we can evaluate. Now our equation, x squared plus y squared, is actually just r squared. So we're evaluating over r squared like we have here. And here you have your integration. So we have in terms of r and theta, we have our function f of x comma y, which turned out to be r for polar coordinates. And don't forget your integration ending. It's always r dr d theta. You multiply in your r's, you get r cubed, and then you can go ahead and continue from there. And I show all of the work. This was pretty easy for integrating. Number 2 took a while. I kept making silly mistakes with the fractions. So be careful with number 2. Number 4, this one's pretty straightforward. 3 integral integration x, y, z. Just remember to work from the inside out. So you first want to work with your x's. So I kind of momentarily ignore the other integrals and just the other bounds and just work with that inner one. And I slowly develop it. And I do this because I always make the silliest mistakes. But you do it however you practiced it, however you feel most comfortable with. I know integrals isn't something we learn in this class. It's something that you should have come with knowledge of. However, I always make the silliest mistakes, so be very, very careful. For 5, same process as number 3, we're working with polar coordinates. Set the triple integral for the volume of sphere rho equals 10 with cylindrical coordinates. So it's actually telling us the radius with this rho equals 10. So that our function is x squared plus y squared plus z squared equals 100. Now when you're working with triple integrals, it's nice to get rid of one variable so that once you get that one variable down, you're back to 2 dimensions instead of 3. So for this one, and for a lot of them, I like to start with z first, unless z looks really ugly. So if we work with z first, we want to create a bound for z. We're working with the sphere, so we know that's just a 3D circle that we're working with. So we want to find the area of this whole circular shape. Okay, so we have our formula x squared plus y squared plus z squared equals 100. Let's solve for z. So we move everything to the other side, we take the square root, and because it didn't tell us that we only want half of the sphere, it didn't limit us at all. So we assume we're working with the entire sphere. So we want plus or minus. So for z, it gives us a bounds of square root of 100 minus r squared and negative square root of 100 minus r squared. We get that r from x squared plus y squared. All right. So now that we got rid of z, we can work on the xy axis. And I should have labeled my axis. So because of that, we can disregard z. I should have said let z equal 0 since that's something that's been sorted out already. So we got rid of that plane. If you look at x squared plus y squared, we have a circle with radius 10. X squared plus y squared gives us to r squared, so we have r10. Now, whenever you're left to find your bounds for a circular figure, we're working with dr d theta. For r, you always look at your center and you work your way out. So we're left with the center point at 0, 0, and we're working our way out to this line. And we know this line is represented with r equals 10. Now we're left to find the angle span of our figure. Because it's our circle, it goes from 0 to 2 pi. And now we have set up our bounds for r and our theta. So we put this all together. We're integrating. We have our z, r, and theta. And we have to incorporate this r. We have this dr d theta that r comes along with it. We weren't told an area for which we were integrating, so we assume they want us to work with one. Otherwise, they would have given us a function for which we're integrating over. So we have r dz dr d theta, and that is our setup. That's all they wanted. So this would be C. And look, be very careful. They all look very similar. So be very careful over the problem solution. And here you have your answers. All right, that's it for test 3. My main concern is that you're comfortable with setting up your bounds for integration and that you know how to go from rectangular to spherical coordinates. And I think those were the new concepts that we learned in this calculus course. Everything else kind of depended on your previous calculus knowledge from Calculus 2, where that was a heavy integration course. All right, thank you.